There are planets where the sky rains molten glass sideways at 7,000 kilometers per hour, and yet, in the mathematics of their existence, there is a stillness that defies comprehension. We begin not with Earth, but with the strangest children of distant stars. Hot Jupiters, gas giants that orbit so close to their parent suns that a year passes in mere days, sometimes in hours. These are worlds that should not exist according to the early models of planetary formation, and yet they do, circling alien stars in configurations that rewrote our understanding of how solar systems come to be. Imagine a planet the size of Jupiter, with its swirling storms and crushing gravity, but positioned where Mercury orbits in our own system. The temperatures soar beyond 1,000 degrees. The atmosphere boils. Metals vaporize and recondense in endless cycles. And yet, despite this chaos, these planets follow their orbits with a precision that has remained unchanged for billions of years. The violence is eternal, but so is the pattern. There is something profoundly calming in that contradiction. A world of fire and wind, locked in a dance so perfect that it will continue long after our sun has died. HD 189733b is one such world. It orbits a star roughly 63 light-years from Earth in the constellation Vulpecula. The planet itself is a deep cobalt blue, a color so vivid it resembles Earth from a distance. But this is no ocean world. The blue comes from silicate particles suspended in the atmosphere, tiny grains of glass that scatter light in the same way our skies do. These particles are caught in winds that scream across the planet at speeds that would obliterate anything in their path. The temperature differential between the day side and the night side creates a jet stream of unimaginable ferocity. And yet, from a great distance, the planet appears serene, a blue marble, silent and still against the black. It is a reminder that violence, when viewed from far enough away, becomes indistinguishable from peace. The storms that rage there have raged for eons. They are not events, they are states of being. And in that permanence, there is a kind of rest. Consider the nature of a hot Jupiter's day. On a planet like HD 209458b, the star it orbits is so close that it fills a quarter of the sky. The light is not the warm yellow glow we know, but a searing white, relentless and inescapable. The planet is tidally locked, meaning one side always faces the star, baking in eternal noon, while the other side is cast in perpetual night. But the atmosphere does not respect this division. Heat flows. Winds carry the energy from day to night and back again, creating a circulation pattern that spans the entire globe. The result is a world in constant motion, yet never changing. The same wind blow, the same heat flows, the same clouds form and dissolve. It is a system in equilibrium, a chaos that has found its rhythm. And in that rhythm there is something almost meditative. The planet does not struggle, it simply is. Hot Jupiters were not supposed to form where we find them. The prevailing theory of planetary formation suggested that gas giants could only coalesce in the cold outer regions of a solar system, where ice and gas were abundant. But observation has shown us otherwise. These giants formed far from their stars, in the distant cold, and then migrated inward, drawn by gravitational interactions with the protoplanetary disk or with other planets. This migration was not gentle. It was a slow, grinding journey that took millions of years, a pilgrimage through the debris and dust of a young solar system. Some planets were ejected entirely, flung into the void to wander as rogues. Others settled into tight, scorching orbits. The process reshaped entire systems, scattering smaller worlds, altering the architecture of planetary families. And yet, once the migration ended, once the planet found its final orbit, the chaos ceased. The system stabilized. The hot Jupiter, now impossibly close to its star, began its eternal circuit. The violence of its formation gave way to the peace of its existence. WASP 12b is one of the most extreme examples. It orbits its star so closely that the star's gravity is tearing the planet apart. The planet is egg-shaped, stretched by tidal forces, and it is losing mass at a rate of about 6 billion tons per second. This material forms a vast, glowing disk around the star, a stream of gas and particles spiraling inward. The planet is being consumed, slowly, inexorably. And yet, this process has been ongoing for millions of years, and it will continue for millions more. The death of WASP 12b is not a sudden catastrophe. It is a slow fade, a gradual dissolution. There is no panic in the physics. The planet does not resist. It simply gives itself to the star, atom by atom, in a process so gradual that it might as well be eternal. Watching this, even in data and models, there is a strange tranquility. The universe does not hurry. Even destruction unfolds at a pace that allows for contemplation. The atmospheres of hot Jupiters are laboratories of exotic chemistry. On Earth, water vapor, nitrogen, and oxygen dominate our skies, but on these distant giants, the air is filled with vaporized metals. Sodium, potassium, iron, magnesium. All of these elements exist as gases, floating in clouds that would be unrecognizable to us. On some planets, it rains iron. On others, the upper atmosphere contains compounds that glow faintly in the starlight, creating auroras that span entire hemispheres. These are not the delicate green curtains we see in our polar skies. These are vast, shimmering veils of light, driven by magnetic fields 1,000 times stronger than Earth's. The auroras pulse and shift, but they never cease. They are a permanent feature, a constant glow in the night, and beneath them the planet turns, indifferent and eternal. One of the most intriguing aspects of hot Jupiters is their silence. There is no solid surface to crash upon, no ocean to churn, no ground to shake. The storms that rage in their atmospheres produce no sound that we would recognize, because sound requires a medium, and the medium here is so alien, so diffuse, that vibrations dissipate into nothing. If you could somehow survive in the upper layers of such a planet, you would witness a maelstrom of unimaginable scale, and yet you would hear nothing. The winds would tear at you, the heat would sear, but the experience would be eerily quiet, a silent apocalypse. This absence of sound, this profound quiet in the midst of chaos, is perhaps the most unsettling and calming aspect of these worlds. They remind us that the universe does not need to announce itself. It simply exists, vast and indifferent, and we are the ones who listen. The discovery of the first hot Jupiter, 51 Pegasi b, in 1995 was a watershed moment in astronomy. For the first time, humanity had confirmed the existence of a planet orbiting a sun-like star beyond our own solar system. The planet was nothing like what anyone expected. It was massive, about half the mass of Jupiter, and it completed an orbit in just over 4 days. The announcement was met with skepticism, then wonder, then a rush to find more. Within a few years, dozens of hot Jupiters had been identified. Each one was unique, yet all shared the same fundamental strangeness. They were giants in places where giants should not be. This discovery forced astronomers to rethink everything. The models were rewritten, the simulations were rerun, and in the process, we learned that the universe is far more creative than we had imagined. The existence of hot Jupiters is a reminder that nature does not follow our expectations. It follows its own rules, and those rules are written in gravity, time, and the slow dance of matter across the void. Some hot Jupiters are so close to their stars that they are being evaporated. The intense radiation strips away the outer layers of the atmosphere, creating a comet-like tail of gas that streams behind the planet as it orbits. This tail can stretch for millions of kilometers, a ghostly plume visible only in certain wavelengths of light. The planet is not dying quickly. It will take billions of years for it to be completely consumed, but it is undeniably fading. And yet, there is no tragedy in this. The planet does not mourn its own dissolution. It simply continues orbit after orbit, losing a little more of itself each time, until one day, in the distant future, it will be gone. This slow vanishing is not an ending. It is a transformation. The atoms that once formed the planet will join the star, or drift into space, or become part of a new world. Nothing is lost. Everything changes. And in that change there is a kind of peace. The study of hot Jupiters has also revealed the incredible diversity of planetary systems. Some hot Jupiters orbit in the opposite direction to their star's rotation, a configuration that suggests a violent past, perhaps a close encounter with another planet that flipped the orbit entirely. Others are part of multi-planet systems, where smaller worlds orbit farther out, untouched by the heat that scorches the inner giant. Each system tells a story, a history written in orbital mechanics and chemical compositions. And each story is different. There is no template for a solar system. There is no standard model. The universe is a place of infinite variation, and hot Jupiters are just one chapter in a much larger tale. The tidal forces acting on hot Jupiters are immense. The star's gravity pulls on the near side of the planet more strongly than the far side, creating a bulge. As the planet rotates, this bulge shifts, generating internal friction that heats the planet from within. This tidal heating is so intense that some hot Jupiters glow with their own infrared light, not just from reflected starlight, but from the heat generated by their own tortured interiors. They are, in a sense, failed stars, too small to ignite fusion, but large enough to generate warmth through compression and friction. This internal glow is faint, invisible to the naked eye, but detectable with sensitive instruments. It is a reminder that even in the coldest reaches of space, there are sources of warmth, hidden fires that burn without flame. Hot Jupiters also challenge our understanding of habitability. For decades, the search for life focused on planets in the Goldilocks zone, the region around a star where temperatures are just right for liquid water. But hot Jupiters, and the systems they inhabit, suggest that habitability might be more complex. Some hot Jupiters have moons, and those moons, if they exist, could be subjected to tidal heating, similar to Jupiter's moon Io. This heating could create subsurface oceans, environments where life in theory could emerge. It is speculative, but not impossible. The universe is full of niches, and life, if it exists elsewhere, may have found ways to thrive in places we have not yet imagined. The presence of hot Jupiters does not preclude life, it simply expands the possibilities. The colours of hot Jupiters are as varied as their chemistries. Some are deep blue, others are brown or red, and a few are nearly black, absorbing almost all the light that strikes them. These colours are determined by the composition of the atmosphere and the temperature. A planet with a lot of sodium will appear yellow. One with vaporized silicates will be blue. A planet with complex hydrocarbons might be dark, almost invisible against the backdrop of space. Each color tells a story about the planet's history, its temperature, its chemistry, and each color, in its own way, is beautiful. These are not the familiar hues of Earth. They are alien, strange, and yet they follow the same physical laws. They are proof that beauty is not unique to our world. It is a property of matter itself, a consequence of light and chemistry, and the way atoms interact. the loneliness of a hot Jupiter is difficult to comprehend. These planets are often the only large body in their inner system, orbiting in isolation, with no companions, no moons, nothing but the star and the void. They are solitary giants, circling endlessly, unchanged and unchanging. There is no one to witness their storms, no one to see their colours shift, no one to measure their winds. They exist in a state of perfect solitude, and yet they are not lonely, because loneliness requires awareness. The planet does not know it is alone. It simply is, and in that simple existence there is a profound calm. The hot Jupiter does not yearn for company. It does not seek purpose. It follows its orbit, and that is enough. As we close this first chapter, consider the paradox of the hot Jupiter, a world of unimaginable violence, and yet, in its constancy, a symbol of peace. The storms will never end, but they will never change. The heat will never fade, but it will never intensify. The planet will continue its orbit day after day, year after year, for billions of years, until the star itself dies and the system is no more. And in that vast span of time, nothing will happen. Everything will happen. The planet will exist, and that existence, in its simplicity, is the most relaxing fact of all. There is no struggle. There is no goal. There is only the orbit, the heat, the wind, and the silence. And in that silence, we find a kind of rest that no earthly place can offer. There are worlds where the ground beneath your feet would be worth more than all the treasures of earth combined, and yet no one will ever walk there. In the constellation Cancer, some 40 light-years from our Sun, orbits a planet designated 55 Cancriae. It is a super-Earth, roughly twice the size of our own world, and it circles its star so closely that a year there lasts only 18 hours. The surface temperature exceeds 2000 degrees Celsius, hot enough to melt rock, hot enough to vaporize metal. But it is not the heat that makes this world extraordinary. It is what lies beneath. Based on the planet's mass and radius, and the composition of its parent star, scientists have theorized that a significant portion of 55 Cancri's interior may be composed of crystalline carbon. Diamond, not scattered gems, but a mantle of compressed carbon, a layer potentially thousands of kilometers thick, wrapped around a core of iron and silicon. The pressures are so immense that carbon atoms are forced into the rigid lattice structure we recognize as diamond. This is not a planet with diamonds. This is a planet made of diamond glittering in the dark, unseen and untouched, a treasure beyond comprehension that will never be claimed. The concept of a diamond planet challenges our terrestrial understanding of value. On Earth, diamonds are rare, formed deep in the mantle under specific conditions of heat and pressure, then brought to the surface by volcanic activity. They are prized for their hardness, their clarity, their ability to refract light into rainbows. But on 55 Cancriae, diamonds are not rare. They are the default state of matter. The entire planet is a monument to pressure and time, a geological process taken to an extreme that our world will never experience. If you could somehow stand on the surface, though you would be instantly incinerated, you would be standing on a crust of graphite and silicates, beneath which lies an ocean of diamond, compressed and heated, until it behaves almost like a fluid. The value we assign to such a world is meaningless. The planet does not care about worth. It simply exists, a sphere of carbon and heat, orbiting in silence. The discovery of 55 Cancri was made through the transit method, observing the slight dimming of the star's light as the planet passed in front of it. This dimming is minuscule, a fraction of a percent, but it is enough. By measuring the timing and depth of these transits, astronomers can determine the planet's size, its orbital period, and, with additional observations, its mass. From mass and size, density can be calculated, and from density, composition can be inferred. The process is indirect, a chain of reasoning built on mathematics and physics, but it is robust. We have never seen 55 Cancri directly. We have never sent a probe there. We have never touched its surface, and yet we know it is there, and we know what it is made of. This knowledge, gained from light and numbers, is one of the quiet triumphs of human curiosity. We reach across the void with instruments and equations, and the universe answers. Diamond planets are not unique. The conditions that create them, high carbon content, extreme pressure, intense heat, are not uncommon in the galaxy. There may be billions of such worlds, scattered among the stars, each one a glittering sphere of compressed carbon, each one utterly indifferent to our existence. They do not shine like stars. They do not emit light. They are dark, silent, and alone, warmed only by the heat of their parent suns and the residual warmth of their own formation. And in that darkness, there is a kind of peace. These planets do not change. They do not evolve. They are what they are, and they will remain so for billions of years until their stars die and the systems fade into cold and dark. Now, shift your gaze to a different kind of world, a planet that does not orbit one sun, but two. These are the circumbinary planets, worlds that circle a pair of stars locked in their own gravitational dance. The most famous of these is Kepler 1.6b, a gas giant roughly the size of Saturn, orbiting two stars in the constellation Cygnus, about 200 light-years from Earth. The stars themselves are a mismatched pair. One is a small, dim red dwarf, the other a slightly larger orange star. They orbit each other every 41 days, and Kepler 1.6b orbits both of them every 229 days. If you could stand on a moon of Kepler 1.6b, assuming such a moon exists, you would witness a double sunset, two suns sinking below the horizon in tandem, one orange, one red, casting overlapping shadows that shift and merge as the stars move. The sky would be a canvas of light and shadow, a perpetual interplay of dual illumination. And when both suns set, the darkness would be profound, broken only by the distant stars and the faint glow of the planet itself. The existence of circumbinary planets was once thought to be unlikely. The gravitational interactions between two stars create a chaotic environment with shifting tidal forces and unstable orbits. It seemed improbable that a planet could form in such conditions, let alone survive. But Kepler 1.6b proved otherwise. The planet orbits in a stable zone, far enough from the binary pair that the gravitational perturbations cancel out, creating a region of relative calm. The orbit is not perfectly circular. It is slightly elliptical, but it is stable, and it has been stable for millions of years. The planet does not wobble. It does not drift. It follows its path with the same precision as any other world, a testament to the fact that even in chaos, order can emerge. The light on a circumbinary planet is unlike anything we experience on Earth. Our sun is a single, constant source of illumination. But on a world like Kepler 1.6b, the light comes from two sources, each with its own color, its own intensity, its own position in the sky. The shadows are doubled, sometimes tripled, depending on the angle. The temperature fluctuates as the planet moves closer to or farther from the binary pair. The seasons, if such a planet has seasons, would be dictated not by axial tilt, but by orbital mechanics, a complex interplay of distance and alignment. And yet, despite this complexity, the system is predictable. The orbits can be calculated, the light levels can be modeled. The chaos is not random. It is structured, governed by the same laws of gravity and motion that govern our own solar system. And in that structure, There is a kind of beauty, a harmony born from complexity. Kepler 16b is not alone. Dozens of circumbinary planets have been discovered, each one orbiting a pair of stars, each one a reminder that the universe is more inventive than our imaginations. Some of these planets are gas giants like Kepler 16b. Others are smaller rocky worlds, super-Earths that orbit in the habitable zones of their binary stars. The possibility of life on such a world is tantalizing. A planet with two suns would receive more light, more energy than a planet orbiting a single star. The increased radiation could drive more complex chemistry, more dynamic weather, more opportunities for life to emerge. Or it could sterilize the surface, the dual bombardment of ultraviolet light, stripping away any atmosphere, leaving the planet barren. We do not yet know, but the question itself is calming, a reminder that the universe is full of possibilities, and we are only beginning to explore them. The stars in a binary system do not remain static. They orbit each other, their positions shifting over time, their light waxing and waning as they eclipse one another. For a planet orbiting such a system, this means that the sky is never the same from one day to the next. The suns rise at different times, set at different angles, create different patterns of light and shadow. There is no monotony here, no repetition. Every day is unique, a new configuration of light and dark, a new dance of celestial bodies. And yet, over the course of years, the patterns repeat. The orbits are periodic. The eclipses are predictable. The chaos resolves into cycles, and the cycles, in their regularity, become a kind of constancy. The planet does not experience randomness. It experiences variation within a framework, and that framework is eternal. One of the most intriguing aspects of circumbinary planets is their formation. How does a planet coalesce in the gravitational turbulence of a binary star system? The prevailing theory suggests that these planets form farther out in the cooler, calmer regions of the protoplanetary disk and then migrate inward, settling into stable orbits around the binary pair. This migration is gradual, driven by interactions with the disk material and the gravitational influence of the stars. It is the same process that creates hot Jupiters, but with an added layer of complexity. The planet must navigate not one gravitational well, but two, threading a path between the stars, finding a balance point where the forces are equal and opposite. It is a delicate process, and many planets likely fail, either crashing into one of the stars or being ejected from the system entirely. But those that succeed, those that find their stable orbits, become permanent residents, circling their twin suns for billions of years. The colors of a binary sunset are determined by the spectral types of the stars. A red dwarf emits most of its light in the red and infrared, giving it a deep crimson hue. A yellow star, like our sun, emits across the visible spectrum, appearing white or pale yellow. A blue giant emits primarily in the blue and ultraviolet, casting a cold electric light. A planet orbiting a red dwarf and a blue giant would experience a sunset of contrasts, one sun sinking in a blaze of red, the other fading in a wash of blue, the two colors blending at the horizon into purples and violets that do not exist in our earthly skies. These are not the warm golden sunsets we know. They are alien, strange, and yet they are governed by the same physics. The light scatters through the atmosphere, the wavelengths separate, the colors emerge. It is the same process, but the palette is different, and the result is a beauty that is entirely its own. The gravitational effects of a binary star system extend beyond the planet itself. If the planet has moons, those moons would experience tidal forces from both the planet and the two stars, creating a complex web of gravitational interactions. The orbits of such moons would be unstable, prone to perturbations and shifts. Some moons might be ejected, flung into space or into the stars. Others might collide with the planet, their material adding to the world's mass. And a few, the lucky few, might find stable orbits, niches where the forces balance, where they can survive for eons. These moons, if they exist, would be worlds of their own, subjected to tidal heating, volcanic activity, perhaps even subsurface oceans. They would be laboratories of geology and chemistry, shaped by forces that no moon in our solar system experiences. And they would be silent, their dramas unfolding in the dark, unseen by any observer. The study of circumbinary planets has also revealed the incredible precision of orbital mechanics. In a system with 2 stars and a planet, there are 3 bodies each exerting gravitational influence on the others. This is the famous 3-body problem, a mathematical challenge that has no general solution. The orbits cannot be predicted with simple equations. They must be simulated, calculated step by step, moment by moment, using computers to track the positions and velocities of each body. And yet, despite the complexity, the systems are stable. The planets do not spiral into the stars. They do not fly off into space. They remain in their orbits, year after year, their paths determined by the initial conditions and the laws of physics. This stability, emerging from chaos, is one of the most profound aspects of celestial mechanics. The universe is not random. It is structured, and that structure, even when complex, is knowable. Imagine the silence of a diamond planet, the stillness of a world where the ground is harder than steel, where the pressures are so great that atoms are locked in place, unable to move, unable to vibrate. There is no sound here, because sound requires motion, and motion requires freedom, and on a diamond planet, there is no freedom. The atoms are prisoners of pressure, held in a lattice so rigid that it will endure for billions of years. And in that rigidity, there is a kind of peace. The planet does not change. It does not erode. It does not weather. It is a monument to permanence, a world that will outlast stars, a testament to the fact that some things once formed are eternal. Now, imagine the light of a binary sunset, the way the 2 suns sink below the horizon, their light mingling, their colours blending, their shadows merging into one. The day does not end all at once. It fades in stages, first one sun, then the other, the sky shifting from bright to dim to dark in a gradual transition that takes hours. And in that transition, there is time to reflect, time to watch, time to simply be. The planet does not rush. The stars do not hurry. The universe unfolds at its own pace, and that pace is slow, deliberate, and infinitely calming. As this chapter closes, consider the diversity of worlds that exist beyond our own. Diamond planets, where the ground is made of gemstones. Circumbinary planets, where the sky holds 2 suns. Each one is different, each one is unique, and yet each one follows the same fundamental laws. Gravity shapes their orbits, pressure determines their composition, light defines their appearance, and in that unity of law there is a profound simplicity. The universe is not arbitrary, it is ordered, and that order, even when it produces the strange and the alien, is a source of deep and abiding calm. These worlds exist, and they will continue to exist long after we are gone, silent and still, waiting in the dark. There are planets where the rain does not fall downward, but sideways, and the droplets are not water, but molten glass, sharpened by wind into microscopic shards that would shred anything in their path. We return to HD 189, 733b, the cobalt blue world we glimpsed in the first chapter, but now we descend deeper into its atmosphere, into the mechanics of its weather. The planet's blue colour is not a trick of distance or a poetic exaggeration. It is real, confirmed by spectroscopic analysis, the result of silicate particles suspended in the upper atmosphere. These particles are tiny, each one smaller than a grain of sand, but there are trillions upon trillions of them, enough to tint the entire planet. They form in the cooler regions of the atmosphere, where temperatures drop just enough for silicon and oxygen to bond, creating glass. But these droplets do not fall gently. The temperature differential between the day side and the night side drives winds that reach speeds of 7,000 kilometers per hour, faster than the speed of sound on Earth. These winds catch the glass particles and hurl them horizontally, creating a perpetual storm of razor-sharp rain that circles the planet in a jet stream of destruction. And yet, from orbit, the planet appears calm, a serene blue sphere, silent and still. The concept of glass rain is difficult to reconcile with our earthly experience. Rain to us is water, falling vertically, driven by gravity, nourishing the ground. It is a gentle process, a cycle of evaporation and condensation that sustains life. But on HD 189, 733b, rain is a weapon. It does not nourish. It erodes, it scours, and it never stops. The glass particles are constantly forming, constantly being swept up by the winds, constantly circling the planet in an endless loop. There is no beginning and no end to this storm. It is a permanent feature of the atmosphere, as much a part of the planet as its gravity or its orbit. And in that permanence, there is a strange kind of stability. The storm does not grow. It does not diminish. It simply is, and it will remain so for as long as the planet exists. The physics of glass rain are governed by temperature and pressure in the hottest regions of the atmosphere. On the day side, the temperatures are so high that silicates remain vaporized, invisible gases mixed with hydrogen and helium. But as the atmosphere circulates, carrying this vapor to the cooler night side, the temperature drops and the silicates condense, forming tiny droplets of molten glass. These droplets are carried by the wind, and as they move, they cool further, solidifying into hard, sharp particles. The wind does not relent. It carries these particles back toward the day side, where they are heated again, vaporized, and the cycle begins anew. It is a process of constant transformation, matter shifting between states, never resting, never settling. And yet, the overall system is in equilibrium. The amount of glass being formed equals the amount being vaporized. The planet does not accumulate material. It does not lose it. It simply circulates it, endlessly, in a loop that has no exit. Now, shift your attention to a different kind of world. A planet not of fire and glass, but of water. Deep ocean worlds, sometimes called ocean planets or water worlds, are hypothesized to exist in great numbers throughout the galaxy. These are planets where the surface is entirely covered by a global ocean hundreds or even thousands of kilometers deep, with no continents, no islands, no land of any kind. The ocean is not like Earth's oceans, confined to basins and bordered by shores. It is total, unbroken, a sphere of water wrapped around a rocky or icy core. The pressure at the bottom of such an ocean would be immense, far greater than the deepest trenches on Earth, enough to compress water into exotic forms of ice that remain solid even at high temperatures. These are not the familiar ice cubes of our freezers. These are high-pressure ices with crystalline structures that do not exist in nature on Earth, ices that sink rather than float, forming a solid layer between the ocean and the core. One candidate for such a world is Kepler 22b, a super-Earth orbiting in the habitable zone of a Sun-like star, about 600 light-years from Earth. The planet is roughly twice the size of Earth, and its density suggests that it could be composed primarily of water. If this is true, then Kepler 22b is not a rocky world with oceans. but an ocean world with a rocky core, a planet where water is the dominant material, where the surface is a featureless expanse of liquid stretching from pole to pole. The temperature at the surface, assuming the planet has a thick atmosphere to trap heat, could be temperate, perhaps even warm, allowing liquid water to exist. But beneath the surface, the ocean would be dark, cold, and still, a vast volume of water pressing down on itself, layer upon layer, until the pressure becomes so great that the water itself transforms. The silence of a deep ocean world is absolute. On Earth, our oceans are filled with sound, the calls of whales, the clicks of dolphins, the rumble of tectonic activity, the crash of waves on distant shores. But on a planet with no land, there are no shores, there are no waves, because waves require wind, and wind requires temperature differentials. And on a world entirely covered by water, the temperature would be remarkably uniform. The ocean would be still, a global reservoir of liquid, undisturbed by currents or tides, unless the planet has a moon to pull at it. And even then, the tides would be gentle, a slow rise and fall of the entire ocean, a breathing motion that takes days to complete. In the depths, far below the reach of sunlight, the water would be utterly dark, utterly quiet, a void of liquid where nothing moves and nothing changes. And in that stillness, there is a peace that is almost incomprehensible. The possibility of life on a deep ocean world is a subject of intense speculation. On Earth, life began in the oceans, and it thrives in the deepest, darkest parts of the sea, around hydrothermal vents where superheated water rich in minerals provides energy for chemosynthetic bacteria. These bacteria form the base of a food chain that includes tube worms, clams, and other creatures that have never seen the sun. If a deep ocean world has a rocky core, and if that core is geologically active, then it could have hydrothermal vents of its own, oases of warmth and chemistry in the cold, dark depths. Life, if it exists on such a world, would be entirely aquatic, adapted to high pressure, low light, and a diet of chemicals rather than sunlight. It would be alien, strange, and yet it would follow the same principles as life on Earth. The need for energy, the drive to reproduce, the struggle to survive. And it would be alone, isolated in an ocean that spans an entire planet, with no other ecosystems, no other environments, no escape. The atmosphere of a deep ocean world would be shaped by the ocean itself. Water vapor would be abundant, creating a thick, humid atmosphere, possibly with dense cloud cover that reflects much of the incoming starlight. The greenhouse effect would be strong, trapping heat and keeping the surface warm. But the atmosphere would also be stable, with little variation in temperature or pressure, because the ocean acts as a thermal buffer, absorbing heat during the day and releasing it at night, smoothing out the extremes. The weather on such a world would be gentle, perhaps a constant drizzle, a light rain that falls from the clouds and merges seamlessly with the ocean below. There would be no storms, no hurricanes, no violent weather events, because there is no land to disrupt the flow of air, no mountains to force the atmosphere upward, no deserts to create temperature gradients. The planet would be calm, quiet, and monotonous, a world where every day is the same as the last. The depth of the ocean on a water world is difficult to visualize. On Earth, the average depth of the ocean is about 4 kilometers. The deepest point, the Mariana Trench, is just under 11 kilometers. But on a planet like Kepler, 22b, the ocean could be hundreds of kilometers deep, perhaps even 1,000. To descend through such an ocean would be to journey through layers of increasing pressure and decreasing light, passing through zones where the water is liquid, then zones where it begins to behave strangely, thickening, becoming more viscous, until finally at the bottom it transitions into high-pressure ice. This ice is not cold, it is hot, heated by the pressure and by the residual warmth of the planet's core. It is a solid, but it is not rigid. It flows slowly over geological timescales, a creeping motion that reshapes the boundary between the ocean and the core, and above it, the ocean presses down a weight so great that it defies comprehension. The color of a deep ocean world as seen from space would depend on the composition of the atmosphere and the ocean itself. If the atmosphere is clear, the planet might appear blue like Earth, the color of water scattering sunlight. But if the atmosphere is thick with clouds, the planet might be white, a featureless sphere reflecting most of the light that strikes it. And if the ocean contains dissolved minerals or organic compounds, the color could shift to green or brown or even red depending on the chemistry. Each color tells a story, a hint at the processes occurring below, the interactions between water, rock, and light. But from a distance, the planet would be serene, a smooth, unbroken surface with no features to distinguish one region from another, no landmarks, no continents, no poles. It would be a world of uniformity, and in that uniformity there is a kind of simplicity that is deeply calming. The tides on a deep ocean world, if the planet has a moon, would be global events. On Earth, tides are local, affecting coastlines and shallow seas, but leaving the deep ocean largely undisturbed. But on a planet with no land, the tides would affect the entire ocean, raising and lowering the surface by meters or even tens of meters, depending on the size and proximity of the moon. The water would rise on the side facing the moon and on the opposite side, pulled by the same gravitational forces. And as the planet rotates, the bulges would move, creating a slow rhythmic sloshing that circles the globe. This motion would be imperceptible to any observer on the surface, because there is no fixed reference point, no shore to measure against. But it would be real, a gentle breathing of the ocean, a pulse driven by gravity and time. The exploration of a deep ocean world would be a challenge unlike any we have faced. On Earth, we have sent probes to the deepest parts of the ocean, but these are brief visits, limited by the crushing pressure and the difficulty of communication. On a planet with an ocean hundreds of kilometers deep, the challenges would be magnified. A probe would need to withstand pressures that would crush steel, navigate in total darkness, and operate autonomously because communication with the surface would be nearly impossible. The water would absorb radio waves, making real-time control unfeasible. The probe would be on its own, descending through the layers, sampling the water, measuring the temperature and pressure, searching for signs of life. And if it reached the bottom, if it touched the high-pressure ice, it would be the first human-made object to do so, a silent ambassador in an alien sea. The loneliness of a deep ocean world is profound. On Earth, even in the most remote parts of the ocean, there is a sense of connection, a knowledge that land is somewhere, that the ocean is part of a larger whole. But on a planet with no land, there is no larger whole. The ocean is everything. It is the entire surface, the entire environment, the entire world. There is no escape, no alternative, no other place to be. And yet, the ocean does not feel confined. It is vast, limitless, a three-dimensional space that extends in all directions, down into the depths, up to the surface, across the globe. It is a world of freedom and isolation, a paradox that defines the nature of such a place. And in that paradox there is a strange kind of peace, a recognition that solitude and vastness are not opposites, but complements. As this chapter closes, consider the diversity of precipitation in the universe. On Earth, rain is water, gentle and life-giving. On HD 189 733b, rain is glass, sharp and deadly. And on a deep ocean world, rain is indistinguishable from the ocean itself, a merging of sky and sea that blurs the boundary between atmosphere and surface. Each form of rain is shaped by the planet's chemistry, its temperature, its atmosphere, and each form in its own way is a reminder that the processes we take for granted, evaporation, condensation, precipitation, are universal, but their expressions are infinitely varied. The universe does not repeat itself. It explores every possibility, every combination, every extreme, and in that exploration, it creates worlds of wonder, worlds of beauty, worlds of profound and abiding calm. There are planets where the sun never moves, frozen in the sky like a painting, and on the opposite side of the world, the stars never fade, locked in an endless night that has no dawn. Tidal locking is one of the most common configurations in the universe, and yet it is one of the most alien to our experience. On Earth, we are accustomed to the rhythm of day and night, the sun rising in the east and setting in the west, the stars appearing and disappearing in a cycle that has governed life for billions of years. But on a tidally locked planet, this rhythm does not exist. The planet's rotation period matches its orbital period exactly, meaning that one side of the planet always faces the star, and the other side always faces away. The day side is locked in perpetual noon, the sun hanging motionless in the sky, its light unrelenting and eternal. The night side is locked in perpetual midnight, the stars fixed in their positions, never rising, never setting, a sky that does not change. And between these two extremes lies the terminator, a narrow band of twilight that circles the planet, a region where the sun sits forever on the horizon, casting long shadows that never move. The mechanism of tidal locking is gravitational. When a planet orbits close to its star, the star's gravity pulls more strongly on the near side of the planet than the far side, creating a tidal bulge. As the planet rotates, this bulge shifts, and the friction generated by this shifting dissipates the planet's rotational energy as heat. Over millions of years, this process slows the planet's rotation until it matches the orbital period, and the bulge becomes fixed, always pointing toward the star. At this point, the planet is tidally locked, and it will remain so for as long as the system exists. The process is slow, gradual, and inevitable. Every planet that orbits close enough to its star will eventually become tidally locked, a prisoner of gravity, its rotation stolen by the very force that holds it in orbit. Proxima Centauri b is one of the most studied tidally locked planets. It orbits Proxima Centauri, the closest star to our Sun, at a distance of just over 4 light-years. The planet is roughly the size of Earth, and it orbits in the habitable zone, the region where temperatures could allow liquid water to exist. But Proxima Centauri is a red dwarf, a small, cool star, and the habitable zone is much closer than it is around our Sun. Proxima Centauri b orbits its star every 11 days, and it is almost certainly tidally locked. This means that one side of the planet is bathed in constant red light, while the other side is frozen in darkness. The temperature difference between the two sides is extreme, potentially hundreds of degrees. And yet, if the planet has a thick atmosphere, that atmosphere could redistribute the heat, carrying warmth from the day side to the night side, creating a band of temperate climate along the terminator, a region where life in theory could exist. The day side of a tidally locked planet is a place of extremes. The sun does not move, and so there are no shadows that shift, no relief from the light, no variation in the intensity of the heat. The ground is scorched, baked by radiation that has been falling on the same spot for billions of years. If the planet has an atmosphere, the air on the day side would be superheated, rising in massive convection currents that carry the heat upward and outward toward the terminator. The sky would be bright, perhaps too bright to look at directly, a dome of light that never dims, and beneath that sky the landscape would be barren, stripped of volatiles, a desert of rock and dust, silent and still. There is no weather here, because weather requires change, and on the day side nothing changes. The sun is eternal, and so is the heat. The night side is the opposite. Here, the sun has never risen, and it never will. The only light comes from the stars, distant and faint, and from the faint glow of the planet's own atmosphere, if it has one. The temperature is far below freezing, cold enough to freeze carbon dioxide, cold enough to turn nitrogen into liquid. If the planet has water, it would be locked in ice, vast glaciers that cover the surface, kilometers thick, untouched by warmth. The sky would be black or perhaps a deep dark blue, depending on the scattering of starlight by the atmosphere. And in that darkness, there would be silence. No wind, because wind requires temperature gradients, and on the night side, everything is uniformly cold. No movement, because there is no energy to drive it. Just stillness, absolute and eternal, a frozen world that will never thaw. The terminator, the boundary between day and night, is the most intriguing region of a tidally locked planet. Here, the sun sits on the horizon, neither rising nor setting, casting a perpetual twilight. The light is dim, but it is constant, a soft glow that illuminates the landscape without the harshness of full daylight. The temperature is moderate, cooler than the day side, warmer than the night side, a balance between the two extremes. If the planet has an atmosphere, the terminator would be a region of constant wind, as air flows from the hot day side to the cold night side, creating a circulation pattern that never stops. This wind would be strong but not violent, a steady breeze that carries heat and moisture, perhaps even clouds, creating weather patterns that are unique to this narrow band. And in this region, if anywhere, life could exist, adapted to the dim light, the constant wind, the unchanging conditions. The concept of a tidally locked habitable zone is a subject of ongoing research. For decades, it was assumed that tidally locked planets could not support life, because the extreme temperature differences would make the surface uninhabitable. But recent climate models have shown that a thick atmosphere could mitigate these extremes, redistributing heat and creating stable conditions along the terminator. The key is atmospheric circulation. If the atmosphere is thick enough, and if the winds are strong enough, heat can be carried from the day side to the night side, preventing the day side from becoming too hot and the night side from becoming too cold. The result is a planet with a habitable band, a ring of temperate climate that circles the world, a region where temperatures are stable, where liquid water could exist, where life could, in theory, emerge. The psychology of living on a tidally locked planet would be profoundly different from life on Earth. On Earth, we measure time by the sun, by the cycle of day and night, by the changing seasons. But on a tidally locked planet, there is no such cycle. The sun does not move. The stars do not change. Time would be measured differently, perhaps by the orbital period, the time it takes for the planet to complete one circuit around its star. But this would be an abstract measure, not tied to any observable change in the sky. The inhabitants of such a world, if they existed, would live in a state of eternal now, with no past and no future, only the present, unchanging and infinite. And in that eternal present, there would be a kind of peace, a freedom from the tyranny of time, a recognition that change is not necessary for existence. The tidal forces acting on a tidally locked planet do not stop once the planet is locked. The star continues to exert gravitational pull, and if the planet's orbit is elliptical, the tidal forces vary over the course of the orbit, creating internal friction that heats the planet from within. This tidal heating can be significant, enough to drive volcanic activity, to melt ice, to create subsurface oceans. Jupiter's moon Io is the most extreme example of tidal heating in our solar system, a world so volcanically active that its surface is constantly being resurfaced by lava. A tidally locked exoplanet in an elliptical orbit could experience similar heating, creating a dynamic interior even as the surface remains locked in place. This internal warmth could provide energy for life, a heat source independent of the star, a furnace buried deep within the planet that never goes out. The observation of tidally locked planets is challenging. Because one side always faces the star, we cannot see the full surface from a single vantage point. The day side is bright, reflecting or emitting light, but the night side is dark, invisible against the blackness of space. To study such a planet, astronomers use a technique called phase curve analysis, observing how the brightness of the planet changes as it orbits its star. When the day side is facing us, the planet is bright. When the night side is facing us, the planet is dim. By measuring these variations, astronomers can infer the temperature difference between the two sides, the composition of the atmosphere, and even the presence of clouds or surface features. It is an indirect method, a way of seeing without looking, of understanding without observing directly. And yet, it works, revealing the secrets of worlds we will never visit. The stability of a tidally locked orbit is remarkable. Once a planet is locked, it remains locked, barring some catastrophic event like a collision with another planet or a close encounter with a rogue star. The tidal forces that created the lock also maintain it, ensuring that the planet's rotation does not drift, that the same side always faces the star. This stability is a form of equilibrium, a balance between gravitational forces and rotational inertia, a state that can persist for billions of years. And in that persistence there is a kind of permanence, a recognition that some configurations, once achieved, are eternal. The planet does not struggle against its fate, it accepts it, and in that acceptance it finds a kind of rest. The colours of a tidally locked planet would be strikingly different on each side. The day side, bathed in constant starlight, would take on the colour of the star. A planet orbiting a red dwarf would have a day side bathed in deep red light, giving the landscape a crimson hue, like a world perpetually at sunset. A planet orbiting a blue star would have a day side bathed in cold electric blue, a landscape of ice and light. The night side, in contrast, would be dark, perhaps black, or perhaps faintly illuminated by the glow of the atmosphere or the reflection of light from the day side. And the terminator, the boundary between the two, would be a gradient, a slow transition from light to dark, a spectrum of colours that shift and blend, creating a twilight zone that is neither day nor night, but something in between. The silence of a tidally locked planet is profound. On the day side there is no change, and without change there is no sound. The wind, if it exists, blows constantly, a background hum that becomes indistinguishable from silence. On the night side there is no movement, and without movement there is no sound. The ice does not crack because it is too cold. The ground does not shift because it is frozen solid, and in the terminator the wind is steady, a constant presence that does not vary, that does not rise or fall, that simply is. This is not the silence of absence, but the silence of constancy, a quiet that comes not from the lack of sound, but from the lack of variation. And in that quiet there is a deep and abiding calm. The exploration of tidally locked planets will be one of the great challenges of the future. These are worlds that are fundamentally different from Earth, with conditions that we have never experienced, with environments that we can barely imagine. To send a probe to such a world would be to venture into the unknown, to explore a place where the rules are different, where the sun does not move, where the stars do not change, where time itself seems to stand still. And yet, the effort would be worth it, because these planets are not rare. They are common, perhaps the most common type of planet in the galaxy. To understand them is to understand the universe, to see the diversity of worlds that exist, to recognize that our own experience is just one possibility among many. As this chapter closes, consider the nature of permanence. On Earth, everything changes. The sun rises and sets, the seasons turn, the landscape erodes and rebuilds. But on a tidally locked planet, change is minimal. The sun does not move, the stars do not shift. The landscape is frozen in place, locked in a configuration that will endure for billions of years. And in that lack of change, there is a kind of peace, a recognition that not everything must evolve, that some things can simply be unchanging and eternal. The tidally locked planet does not struggle, it does not strive, it simply exists, and in that existence, it finds a rest that is absolute and complete. There are planets that absorb nearly all the light that touches them, reflecting less than 1% back into space, darker than the darkest material on Earth, invisible against the void. Tree S. 2b is the darkest planet ever discovered. It orbits a Sun-like star about 750 light-years from Earth, in the constellation Draco. The planet is a hot Jupiter, slightly larger than Jupiter itself, and it orbits so close to its star that its surface temperature exceeds 1000 degrees Celsius. And yet, despite being bathed in intense starlight, TRAES 2b reflects less than 1% of the light that strikes it. It is darker than coal, darker than asphalt, darker than any paint or pigment we have ever created. The planet absorbs the light, trapping it in its atmosphere, converting it to heat. The exact mechanism is not fully understood, but it is believed that the atmosphere contains light-absorbing chemicals, perhaps vaporized sodium, potassium, or titanium oxide, compounds that capture photons and prevent them from escaping. The result is a planet that is nearly invisible, a shadow against the stars, a void in the shape of a sphere. The darkness of TRAES 2b is not absolute. The planet does emit a faint red glow, the result of its own internal heat, the warmth generated by the absorption of starlight and by tidal forces. This glow is too faint to see with the naked eye, but it can be detected with sensitive instruments, a dim ember in the blackness. The glow is not reflected light, it is emitted light, the planet's own radiation, a sign that, even in darkness, there is warmth. And in that warmth, there is a kind of presence, a reminder that the planet is not empty, not dead, but alive with energy, even if that energy is invisible. The darkness is not the absence of light, it is the transformation of light, the conversion of photons into heat, a process that makes the planet a furnace wrapped in shadow. The concept of albedo, the measure of how much light a surface reflects, is central to understanding dark planets. Earth has an albedo of about 30%, meaning that 30% of the sunlight that strikes our planet is reflected back into space. The Moon has an albedo of about 12%, which is why it appears grey. Fresh snow has an albedo of up to 90%, reflecting almost all the light that hits it. But TRAES 2b has an albedo of less than 1%, making it one of the least reflective objects in the known universe. This low albedo is not due to the planet's composition alone, but to the interaction between the starlight and the atmosphere, a complex chemistry that we are only beginning to understand. The planet is a laboratory of light and matter, a place where photons are captured and transformed, where darkness is not passive, but active. Now, shift your attention to a different kind of darkness. Not the darkness of absorption, but the darkness of isolation. Rogue planets, also called free-floating planets or orphan planets, are worlds that do not orbit any star. They wander through the galaxy alone, untethered, drifting through the void with no sun to warm them, no light to illuminate them. These planets were either ejected from their original solar systems during the chaotic early stages of planetary formation, or they formed in isolation, condensing from clouds of gas and dust without ever being captured by a star. They are cold, dark, and silent, traveling through space at speeds of tens of kilometers per second, following trajectories that will carry them across the galaxy for billions of years. The number of rogue planets in the Milky Way is staggering. Recent estimates suggest that there may be billions of them, perhaps even more rogue planets than stars. They are difficult to detect because they emit no light of their own and they do not reflect light from a nearby star. They are invisible, ghosts in the dark, detectable only through their gravitational influence or through the faint infrared radiation they emit as they slowly cool. The discovery of rogue planets has been made possible by gravitational microlensing, a technique that detects the bending of light from a distant star as a rogue planet passes in front of it. The effect is brief, lasting only hours or days, but it is unmistakable, a signature of mass moving through space. The temperature of a rogue planet is determined by its internal heat, not by any external source. When a planet forms, it is hot, the result of gravitational compression and the decay of radioactive elements in its core. Over time, this heat radiates away, and the planet cools. But the cooling is slow, taking billions of years. A rogue planet the size of Jupiter could retain enough internal heat to maintain a surface temperature above the freezing point of water for millions of years after being ejected from its system. Beneath the surface, in the deep interior, the temperature could remain high enough to sustain a liquid ocean, insulated by layers of ice and rock. This ocean would be dark, heated from below by geothermal energy, a hidden sea in a wandering world, isolated from the rest of the universe. The possibility of life on a rogue planet is remote, but not impossible. On Earth, life exists in the deepest parts of the ocean, around hydrothermal vents, where sunlight never reaches. These ecosystems are powered by chemical energy, not by photosynthesis, and they are entirely independent of the sun. A rogue planet with a subsurface ocean and active geology could in theory support similar life, organisms adapted to darkness, to cold, to isolation. Such life would be fundamentally different from anything on Earth, not because of its biology, but because of its context. It would exist on a world with no star, no seasons, no external reference point, a world that is entirely self-contained. And it would be alone, utterly and completely, with no possibility of contact, no chance of discovery, drifting through the galaxy in silence. The loneliness of a rogue planet is absolute. On a planet orbiting a star, there is at least the presence of the star, a source of light and heat, a fixed point in the sky. But a rogue planet has no such anchor. The stars are distant, faint, scattered across the sky in patterns that shift imperceptibly over millennia. There is no day, no night, no cycle of any kind. The planet simply drifts, moving through space at a constant velocity, following a path determined by the gravitational interactions of its past. It does not know where it is going. It does not know where it has been. It simply is, a wanderer in the dark, with no destination and no purpose. The discovery of rogue planets has profound implications for our understanding of planetary formation. The traditional model suggests that planets form in the protoplanetary disk around a young star, gradually accreting material until they reach their final size. But the existence of billions of rogue planets suggests that this process is far more chaotic than we thought. Planets are not just formed, they are also destroyed, ejected, scattered. The early solar system was a violent place, with planets colliding, merging, and being flung into interstellar space. The planets we see today are the survivors, the ones that found stable orbits and avoided catastrophe. But for every planet that survived, there may be dozens that did not, cast out into the void to wander alone. The speed of a rogue planet is determined by the circumstances of its ejection. A planet ejected by a close encounter with a gas giant could be traveling at speeds of up to 50 kilometers per second, fast enough to escape the gravitational pull of the galaxy itself, becoming an intergalactic wanderer. Most rogue planets, however, travel at slower speeds, around 10 to 20 kilometers per second. fast enough to cross the galaxy in a few 100 million years, but not fast enough to escape it. They are bound to the Milky Way, circling the galactic center in vast, elongated orbits, passing through the spiral arms, through the voids between the stars, through regions of space that are empty and silent. The atmosphere of a rogue planet, if it has one, would be frozen. Without the heat of a star, the gases that make up the atmosphere, nitrogen, methane, carbon dioxide, would condense into ice, falling to the surface in a slow, steady rain that would continue for millions of years. Eventually, the atmosphere would be gone, collapsed onto the surface as a layer of frost, leaving the planet airless, a ball of ice and rock drifting through space. But if the planet is large enough, and if it has enough internal heat, the atmosphere could be sustained, kept in a gaseous state by the warmth rising from below. Such an atmosphere would be thin, cold, and still, but it would be there, a tenuous envelope of gas surrounding a world that has no sun. The colour of a rogue planet, if it could be seen, would depend on its composition. A planet covered in water ice would be white or pale blue, reflecting the faint starlight. A planet with a rocky surface would be grey or brown, the colour of stone and dust. A planet with a thick atmosphere of methane or ammonia could be orange or yellow, the gases scattering light in the same way they do on Jupiter or Saturn. But in the absence of a nearby star, these colours would be muted, barely visible, a faint suggestion of hue in the overwhelming darkness. The planet would be a ghost, a shadow, a presence, felt more than seen. The silence of a rogue planet is the silence of deep space. There is no atmosphere to carry sound, no surface to vibrate, no activity to generate noise. The planet is utterly quiet, a stillness so complete that it is almost tangible. And in that silence, there is a kind of peace, a recognition that not all places are meant to be loud, that some corners of the universe are meant to be quiet, to exist in a state of rest that is undisturbed and eternal. The rogue planet does not call out, it does not signal. It simply drifts, a silent traveller in an infinite sea. The future of a rogue planet is uncertain. It could wander the galaxy for billions of years, never encountering another star, never being captured by a solar system, simply drifting until the universe itself grows cold and dark. Or it could, by chance, pass close to a star and be captured by its gravity, becoming part of a new solar system, a new family of worlds. The odds of such a capture are low, but they are not zero. In the vastness of space, over the immensity of time, even unlikely events become inevitable. A rogue planet could find a new home, a new star to orbit, a new purpose. Or it could remain alone, a wanderer forever, a testament to the fact that not all journeys have destinations. The study of rogue planets is still in its infancy. We have detected only a handful of them, and our understanding of their properties is limited. But as our instruments improve, as our techniques become more refined, we will find more. We will map their distribution, measure their masses, study their compositions. And in doing so, we will learn more about the history of our own solar system, about the violence and chaos that shape the planets we see today. The rogue planets are not anomalies. They are the norm, the natural consequence of planetary formation, a reminder that the universe is a place of constant change, where nothing is permanent, and everything is in motion. As this chapter closes, consider the nature of darkness and solitude. Try ES. 2b is dark, but it is not alone. It orbits a star, bathed in light that it absorbs and transforms. Rogue planets are alone, but they are not entirely dark. They glow faintly with their own heat, a warmth that will persist for eons. Both are extremes, both are alien, and yet both are part of the same universe, governed by the same laws, shaped by the same forces. And in their extremes, they remind us that the universe is vast, diverse, and endlessly surprising, a place where darkness and light, solitude and companionship are not opposites but complements, different expressions of the same fundamental reality. There are planets where the clouds are not made of water vapor, but of rubies and sapphires, crystalline particles that drift through the atmosphere, catching the light of distant suns and scattering it into colors we have never seen. HAT-P 7b is a gas giant located about 1,000 light-years from Earth in the constellation Cygnus. It is a hot Jupiter, orbiting its star so closely that a year there lasts only 2 days. The temperatures in the upper atmosphere exceed 2,000 degrees Celsius, hot enough to vaporize most metals. But it is not the heat that makes this planet extraordinary. It is the clouds. Observations have revealed that the atmosphere of HAT-P 7b contains clouds made of corundum, the mineral that forms rubies and sapphires on Earth. These clouds are not the soft, billowing formations we see in our skies. They are made of tiny crystals, each one a fragment of gemstone, suspended in the superheated air. The crystals form on the cooler night side of the planet, where temperatures drop just enough for aluminum oxide to condense, and then they are carried by winds to the day side, where they evaporate back into gas. The result is a planet with clouds that glitter, that shimmer, that catch the starlight and refract it into a spectrum of colours, a sky filled with jewels. The formation of corundum clouds is a process of temperature and chemistry. Corundum is aluminum oxide, a compound that is stable at high temperatures, but only condenses into solid form when the temperature drops below a certain threshold. On HAT-P 7b, the day side is too hot for corundum to exist as a solid, but the night side is just cool enough. As the atmosphere circulates, carrying gas from the day side to the night side, the aluminum oxide condenses into tiny crystals, forming clouds. These clouds are then swept back toward the day side by the planet's powerful winds, and as they enter the hotter regions, they evaporate, releasing the aluminum and oxygen back into the atmosphere. The cycle is continuous, a perpetual transformation of matter between gas and solid, a dance of chemistry that has been ongoing for billions of years. The color of corundum depends on trace impurities. Pure corundum is colorless, but the addition of chromium creates rubies, deep red crystals that have been prized by humans for millennia. The addition of iron and titanium creates sapphires, which can be blue, yellow, green, or even pink, depending on the exact composition. On HAT-P 7b, the corundum clouds likely contain a mix of these impurities, creating a palette of colors that shifts and changes as the crystals form and dissolve. The clouds are not uniform. They are patchy, variable, a mosaic of colors that depends on the local chemistry, the temperature, the wind patterns. And from a distance, the planet would appear to shimmer, its appearance changing over time as the clouds move and evolve. A world that is never quite the same from one moment to the next. Now, turn your attention to a different class of worlds. Super-Earths, planets larger than Earth but smaller than Neptune, are among the most common types of planets in the galaxy. They range in size from about 1.5 to 10 times the mass of Earth, and they can be rocky, icy, or a combination of both. The term super-Earth is somewhat misleading because these planets are not simply larger versions of our own world. They are fundamentally different, with higher gravity, thicker atmospheres, and geological processes that we do not fully understand. Some super-Earths orbit in the habitable zones of their stars, where temperatures could allow liquid water to exist. Others orbit too close, becoming scorched worlds with molten surfaces, and still others orbit too far, becoming frozen ice balls, silent and still. Kepler 452b is one of the most intriguing super-Earths. It orbits a sun-like star in the constellation Cygnus, about 1,400 light-years from Earth. The planet is about 60% larger than Earth, and it orbits in the habitable zone at a distance where the temperature could support liquid water. The orbital period is 385 days, remarkably similar to Earth's year. The star itself is slightly older and slightly larger than our Sun, but it is close enough in type that Kepler 452b has been called Earth's cousin. We do not know if the planet is rocky or if it has an atmosphere, because it is too far away to study in detail, but the possibility that it could be habitable, that it could have oceans, continents, perhaps even life, is tantalizing. It is a reminder that Earth is not unique, that the conditions that allow life to exist may be common, scattered across the galaxy on worlds we have not yet seen. The gravity on a super-Earth would be significantly higher than on Earth. A planet with twice the mass of Earth would have a surface gravity about 1.5 times stronger, meaning that a person who weighs 70 kilograms on Earth would weigh over 100 kilograms on such a world. This increased gravity would affect everything. The atmosphere would be thicker, held more tightly to the surface. The mountains would be lower, unable to rise as high before collapsing under their own weight. The oceans would be deeper, the pressure at the bottom far greater than anything on Earth. And life, if it existed, would be adapted to this higher gravity, with stronger bones, more robust muscles, a physiology shaped by the constant pull of the planet. The atmosphere of a super-Earth could be vastly different from our own. With higher gravity, the planet could retain lighter gases like hydrogen and helium, gases that Earth lost early in its history. The result could be a thick, dense atmosphere, perhaps hundreds of kilometers deep, with pressures at the surface far greater than on Earth. Such an atmosphere would create a powerful greenhouse effect, trapping heat and raising the surface temperature. But it could also protect the surface from radiation, shielding any life below from the harmful effects of cosmic rays and solar flares. The balance between heat retention and radiation protection would determine the habitability of the planet, a delicate equilibrium that depends on the composition of the atmosphere, the distance from the star, and the planet's own internal heat. The geology of a super-Earth would be more active than Earth's. The higher gravity would create greater pressures in the interior, driving more vigorous convection in the mantle, more intense volcanic activity, more frequent earthquakes. The tectonic plates, if they exist, would move faster, collide more violently, creating mountain ranges that rise and fall on timescales of millions of years rather than hundreds of millions. The planet would be a dynamic place, constantly reshaping itself, constantly in motion. And yet, this activity would not be chaotic. It would be governed by the same physical laws that govern Earth, the same principles of heat transfer, pressure, and material strength. The planet would be different, but it would not be alien. It would be a variation on a theme, a different expression of the same fundamental processes. The possibility of life on a super-Earth is a subject of intense debate. On one hand, the higher gravity, thicker atmosphere, and more active geology could create conditions that are hostile to life as we know it. On the other hand, these same factors could create a more stable environment, with a stronger magnetic field to protect against radiation, a thicker atmosphere to regulate temperature, and more geothermal energy to drive chemical reactions. Life is adaptable, and it has emerged on Earth in environments that were once thought to be uninhabitable, in boiling hot springs, in the frozen wastes of Antarctica, in the crushing depths of the ocean. If life can exist in these extremes on Earth, it is not unreasonable to think that it could exist on a super-Earth, adapted to the unique conditions of such a world. The clouds on a super-Earth could be as varied as the clouds on Earth, but with different compositions. On a planet with a hydrogen-rich atmosphere, the clouds could be made of ammonia or methane, similar to the clouds on Jupiter or Saturn. On a planet with a thick carbon dioxide atmosphere, the clouds could be made of sulfuric acid, like the clouds on Venus. and on a planet with conditions similar to Earth, the clouds could be made of water vapor, forming rain, snow, and ice, just as they do here. But the thickness of the atmosphere, the strength of the gravity, and the intensity of the sunlight would all affect the behavior of these clouds, creating weather patterns that are unique to each world. The clouds would not just be decorations in the sky, they would be active participants in the planet's climate, shaping the temperature, the precipitation, the distribution of heat and moisture. The study of super-Earths is one of the most active areas of exoplanet research. Thousands of super-Earths have been discovered, and each one is different, each one a new puzzle to solve. Some are hot, some are cold, some are rocky, some are icy, and some are covered in oceans. The diversity is staggering, and it challenges our understanding of planetary formation and evolution. Why are super-Earths so common in the galaxy when there are none in our own solar system? What processes create them? What determines their composition? These are questions that astronomers are working to answer, using observations, models, and simulations to piece together the story of these worlds. The colors of a super-Earth would depend on its atmosphere and surface. A planet with a thick, clear atmosphere and a rocky surface could appear brown or grey, the color of stone and dust. A planet with oceans could appear blue, like Earth, the color of water scattering sunlight. A planet with a thick atmosphere of methane could appear orange or yellow, the gas absorbing red light and reflecting the rest. And a planet with clouds of corundum, like HAT P7b, could appear to shimmer, its color shifting and changing as the clouds move and evolve. Each color is a clue, a piece of information about the planet's composition, its temperature, its atmosphere. And each color, in its own way, is beautiful, a testament to the diversity of worlds that exist in the universe. The silence of a super-Earth, if it has a thick atmosphere, would be different from the silence of space. Sound would travel through the air, but the density of the atmosphere would affect the speed and quality of the sound. On a planet with a very thick atmosphere, sound could travel faster, and it could carry farther, creating an acoustic environment that is unlike anything on Earth. The wind, if it exists, would be a constant presence, a low hum or roar that fills the air, a background noise that is always there, always the same. And in that constancy, there would be a kind of peace, a recognition that the planet is alive, that it is active, that it is not a dead, silent ball of rock, but a world with its own rhythms, its own patterns, its own voice. The future exploration of super-Earths will require new technologies, new instruments, new ways of observing and analyzing distant worlds. We will need telescopes powerful enough to detect the faint light reflected by these planets, spectrometers sensitive enough to analyze their atmospheres, and models sophisticated enough to interpret the data. And we will need patience because the study of exoplanets is a slow process, a gradual accumulation of knowledge, a step-by-step journey toward understanding. But the effort is worth it, because super-Earths are not rare. They are common, perhaps the most common type of planet in the galaxy. To understand them is to understand the universe, to see the full range of possibilities, to recognize that our own world is just one example among many. As this chapter closes, consider the beauty of diversity. Jewel clouds of corundum drifting through superheated skies, super-Earths with gravity that would crush us, atmospheres that would suffocate us, and yet, perhaps, life that thrives in conditions we cannot imagine. Each world is unique, each world is different, and yet each world is governed by the same laws, shaped by the same forces, a variation on the same fundamental theme. And in that variation, there is a kind of harmony, a recognition that the universe is not monotonous, not repetitive, but endlessly creative, endlessly inventive, a place where every possibility is explored, every combination is tried, every extreme is realized. There are planets where a year passes in less time than it takes to watch a film, and others where a single season lasts longer than all of recorded human history. The speed at which a planet orbits its star is determined by a simple relationship. The closer the planet is to the star, the faster it must move to maintain its orbit. This is a consequence of gravity, the same force that keeps the Moon circling Earth and Earth circling the Sun. But the range of orbital speeds in the universe is staggering. From planets that complete an orbit in a matter of hours, to planets whose years span centuries. Each extreme creates a different experience of time, a different rhythm of existence, a different relationship between the planet and its star. And in that diversity, there is a reminder that time itself is not absolute, but relative, shaped by motion and gravity. The fastest known orbit belongs to a planet designated K2, 137b, a rocky world about the size of Earth, orbiting a red dwarf star about 200 light-years away. The planet completes one orbit in just 4 hours and 18 minutes. This is faster than the rotation of Earth, faster than the orbit of the International Space Station, faster than anything we experience in our daily lives. The planet is so close to its star that the surface temperature exceeds 2000 degrees Celsius, hot enough to vaporize rock. The gravity of the star pulls at the planet with immense force, and the planet responds by moving at speeds of over 400 kilometers per second, a velocity that is almost incomprehensible. And yet, despite this speed, the orbit is stable, unchanging, a perfect balance between the inward pull of gravity and the outward momentum of motion. The experience of time on K2, 137b would be profoundly different from our own. A year there lasts only a few hours, meaning that the concept of a year, as we understand it, would be meaningless. There would be no seasons, no long-term cycles, no sense of progression from one state to another. The planet would exist in a state of perpetual now, with no past and no future, only the present moment, repeated endlessly. And yet, this does not mean that time does not pass. It simply passes differently, measured not in years or months, but in hours and minutes, a rapid ticking of the cosmic clock that never slows, never stops. Now, shift your attention to the opposite extreme. PSR Bone 62026b, also known as Methuselah, is one of the oldest known planets in the universe, and it has one of the longest orbital periods. The planet orbits a binary system consisting of a pulsar and a white dwarf, located in the globular cluster M4, about 12,000 light-years from Earth. The planet is roughly the size of Jupiter, and it takes about 100 years to complete a single orbit. This means that a being living on such a planet would experience only a handful of years in a human lifetime, perhaps only 1 or 2. The seasons, if such a planet has seasons, would last decades. The changes in the sky, the shifting positions of the stars, would be imperceptible on human timescales, visible only over generations. The orbital period of a planet is intimately connected to its distance from the star. Kepler's third law states that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. This means that if you double the distance from the star, the orbital period increases by a factor of about 2.8. If you triple the distance, the period increases by a factor of about 5.2. The relationship is not linear, but exponential, and it means that planets in the outer reaches of a solar system move much more slowly than planets close to the star. This is why Mercury, the closest planet to our Sun, completes an orbit in just 88 days, while Neptune, the farthest, takes 165 years. The concept of a season is tied to the axial tilt of a planet. Earth is tilted at an angle of about 23 degrees relative to its orbital plane. and as Earth orbits the Sun, different parts of the planet receive more or less direct sunlight, creating the cycle of spring, summer, autumn, and winter. But on a planet with a very long orbital period, the seasons would be correspondingly long. On a planet that takes a century to orbit its star, each season would last about 25 years. A being born in spring would live through summer, autumn, and winter, and perhaps see the return of spring, but only if they lived a full human lifespan. The experience of such a world would be one of slow, gradual change, a progression so gentle that it would be almost imperceptible from day to day, but undeniable over the course of a lifetime. Uranus, in our own solar system, offers a glimpse of extreme seasonal variation. The planet is tilted at an angle of 90 to 8 degrees, meaning that its axis of rotation is nearly parallel to its orbital plane. This extreme tilt causes each pole to experience 42 years of continuous sunlight, followed by 42 years of continuous darkness, as the planet completes its 84-year orbit around the Sun. The result is a world where the concept of day and night as we understand it is replaced by decades of light and decades of dark. The temperature variations are extreme, and the weather patterns are unlike anything on Earth, driven by the slow, inexorable shift of sunlight from one hemisphere to the other. And yet, despite these extremes, Uranus remains in its orbit, stable and predictable, a testament to the fact that even the strangest configurations can endure. The speed of a planet's orbit also affects its climate. A planet that orbits quickly, completing a year in a matter of days or hours, does not have time for seasonal variations to develop. The temperature is determined primarily by the distance from the star and the composition of the atmosphere, not by the position in the orbit. But a planet with a long orbital period, especially one with an elliptical orbit, can experience significant seasonal changes. When the planet is closest to the star, at perihelion, it receives more sunlight, and the temperature rises. When it is farthest from the star, at aphelion, it receives less sunlight, and the temperature falls. The difference can be dramatic, creating a world where the climate swings between extremes over the course of a single orbit. Mars offers an example of this effect. The planet's orbit is more elliptical than Earth's, and the difference in solar radiation between perihelion and aphelion is about 45%. This variation, combined with the planet's axial tilt, creates seasons that are more extreme than those on Earth. The southern hemisphere of Mars experiences short, hot summers when the planet is closest to the Sun, and long, cold winters when it is farthest away. The northern hemisphere experiences the opposite, long, mild summers and short, cold winters. The result is a planet with a climate that is highly variable, not just from season to season, but from year to year, as the position of perihelion slowly shifts over time due to gravitational interactions with other planets. The fastest orbits are found around the smallest stars. Red dwarfs, the most common type of star in the galaxy, are much smaller and cooler than our Sun, and their habitable zones are correspondingly closer. A planet in the habitable zone of a red dwarf might orbit at a distance of only a few million kilometers, compared to the 150 million kilometers that separate Earth from the Sun. At such close distances, the orbital periods are short, often just a few days or weeks. This proximity has consequences. The planets are likely to be tidally locked, with one side always facing the star, and they are subjected to intense stellar activity, including flares and radiation bursts that could strip away atmospheres or sterilize surfaces. And yet, despite these challenges, red dwarf systems are prime targets in the search for habitable planets, because red dwarfs are so numerous, and because their small size makes it easier to detect the planets that orbit them. The longest orbital periods are found in the outer regions of solar systems, or in planets that orbit binary stars or stellar remnants. These planets move slowly, taking decades, centuries, or even millennia to complete a single orbit. The experience of such a world would be one of profound stillness, a sense that nothing changes, that the universe is frozen in place. The stars would appear fixed in the sky, their positions shifting only imperceptibly over the course of a lifetime. The seasons, if they exist, would be so long that they would span generations, creating cultures and societies that are defined by the season they are born into, with no expectation of seeing another. And yet, the orbit continues, the planet moves, and over the vast expanse of time the cycle completes and begins again. The study of orbital mechanics is one of the oldest branches of astronomy, dating back to the work of Kepler and Newton. The laws that govern planetary motion are simple, elegant, and universal, applying to every planet, every moon, every object in orbit around another. These laws allow us to predict the positions of planets with extraordinary precision, to calculate eclipses centuries in advance, to send spacecraft to distant worlds with pinpoint accuracy. And yet, despite this precision, there is a beauty in the diversity of orbits, a recognition that the same laws can produce an infinite variety of outcomes, from the rapid dance of K2 137b to the slow waltz of Methuselah. The psychological impact of living on a planet with an extreme orbital period would be profound. On a world where a year lasts only hours, the concept of long-term planning would be meaningless. There would be no time to grow crops, no time to build civilizations, no time to develop cultures. Life, if it existed, would be adapted to rapid cycles, to quick bursts of activity, to a pace that is almost frantic. On a world where a year lasts centuries, the opposite would be true. Long-term planning would be essential, but it would also be abstract, disconnected from immediate experience. A project begun in one season might not be completed until the next, decades later. The inhabitants of such a world would live in a state of deep time, where change is slow, where patience is not a virtue but a necessity. The colours of a planet's sky would change with the seasons, if the planet has an atmosphere and an axial tilt. On Earth, the angle of the sunlight affects the colour of the sky, creating the deep blues of summer and the pale washed-out hues of winter. On a planet with extreme seasons, these changes would be more pronounced. A sky that is bright and clear in summer might become dark and hazy in winter, as the angle of the sunlight changes and the atmosphere responds. And on a planet with a very long orbital period, these changes would unfold over decades, a slow transformation that is almost imperceptible from day to day, but undeniable over the course of a lifetime. The silence of a planet with a slow orbit is the silence of deep time. There is no rush, no urgency, no sense that anything must happen quickly. The planet moves at its own pace, following its orbit with a patience that is almost meditative. The stars do not hurry, the seasons do not rush. The universe unfolds slowly, deliberately, and in that slowness there is a kind of peace. The planet does not struggle against its orbit. It does not resist the pull of gravity. It simply moves, and in that movement it finds a rhythm that is eternal, unchanging, and profoundly calming. As this chapter closes, consider the nature of time. On Earth, we measure time by the sun, by the cycle of day and night, by the changing seasons. But on other worlds, time is measured differently, in hours or in centuries, in rapid cycles or in slow progressions. And yet, time itself is the same, a dimension of the universe that flows at a constant rate, unaffected by our perception of it. The planets do not experience time, they simply exist within it, moving through space, following their orbits, indifferent to the passage of seconds, minutes, years, or millennia. And in that indifference, there is a profound lesson, that time is not something to be rushed or feared, but something to be accepted, a river that carries us forward, whether we move quickly or slowly, whether we resist or surrender. There was a time not long ago when humanity believed that the planets of our solar system were the only worlds that existed, and the idea that other stars might host their own families of planets was nothing more than speculation. The search for planets beyond our solar system began in earnest in the late 20th century, but the dream is much older. For centuries, philosophers and astronomers wondered whether the stars in the night sky were distant suns, and whether those suns might have planets of their own. The question was profound, but the tools to answer it did not exist. Planets do not emit light. They only reflect the light of their stars, and at interstellar distances, that reflected light is impossibly faint, drowned out by the brilliance of the star itself. To detect a planet orbiting another star would require instruments of extraordinary sensitivity, techniques of remarkable precision, and patience measured in decades. And yet, humanity persisted, driven by the simple desire to know, are we alone? The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995, when astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b. The planet was detected using the radial velocity method, which measures the tiny wobble in a star's motion caused by the gravitational pull of an orbiting planet. The wobble is small, a shift in velocity of only a few meters per second. But it is detectable through the Doppler effect, the same phenomenon that causes the pitch of a siren to change as it moves toward or away from you. The discovery was revolutionary. It proved that planets existed beyond our solar system, and it opened the door to a new era of astronomy. Within a few years, dozens of exoplanets had been discovered. Within a decade, hundreds, and today, the count stands at over 5,000 confirmed planets, with thousands more candidates awaiting verification. The methods used to detect exoplanets are varied, each one suited to different types of planets and different observing conditions. The radial velocity method is effective for detecting massive planets in close orbits, because these planets cause the largest wobbles in their stars. The transit method, which measures the dimming of a star's light as a planet passes in front of it, is effective for detecting planets of all sizes, as long as the orbit is aligned edge-on to our line of sight. Gravitational microlensing detects planets by the way their gravity bends the light of a background star, a technique that is sensitive to planets at great distances from their stars, and even to rogue planets that orbit no star at all. And direct imaging, the most challenging method, captures actual photographs of planets by blocking out the light of the star, revealing the faint glow of the planet itself. Each method has its strengths and weaknesses, and together they have revealed a universe far more diverse than anyone imagined. The Kepler Space Telescope, launched in 2009, was a turning point in the search for exoplanets. The telescope was designed to stare at a single patch of sky, monitoring the brightness of over 150,000 stars, looking for the telltale dimming that indicates a planet passing in front of its star. Over the course of its mission, Kepler discovered over 2,700 confirmed planets and identified thousands more candidates. The data revealed that planets are common, that nearly every star in the galaxy has at least one planet, and that the diversity of planetary systems is staggering. There are hot Jupiters and super-Earths, ocean worlds and lava planets, systems with one planet and systems with 7. The universe, it turns out, is not a barren place. It is teeming with worlds, each one unique, each one a variation on the theme of planetary formation. The discovery of exoplanets has profound implications for the question of life. For decades, the search for extraterrestrial life was constrained by the fact that we had only one example of a habitable planet, Earth. But now, we know that there are billions of planets in the galaxy, and many of them orbit in the habitable zones of their stars, where temperatures could allow liquid water to exist. The presence of liquid water is not a guarantee of life, but it is a prerequisite at least for life as we know it. And the sheer number of potentially habitable planets suggests that the conditions for life may be common, that we are not unique, that somewhere, in the vastness of space, there may be other worlds where life has emerged, evolved, and perhaps even developed intelligence. The search for biosignatures, the chemical or physical signs of life, is one of the most exciting frontiers in astronomy. Future telescopes, like the James Webb Space Telescope and the proposed Habitable Exoplanet Observatory, will be able to analyze the atmospheres of distant planets, looking for gases like oxygen, methane, or ozone, which on Earth are produced by living organisms. The detection of such gases would not be proof of life, because they can also be produced by geological processes, but it would be a strong hint, a clue that life might exist. And even if we do not find life, the search itself is valuable because it teaches us about the conditions that allow life to emerge, the factors that make a planet habitable, and the diversity of environments that exist in the universe. The future of planetary exploration is not limited to observation. Humanity has already sent probes to every planet in our solar system, and to many of their moons. We have landed on Mars, Venus, and Titan. We have flown past Pluto and the Kuiper Belt, and we have plans to go farther, to send missions to the outer reaches of the solar system, to study the ice giants, to explore the moons of Jupiter and Saturn, to search for life in the subsurface oceans of Europa and Enceladus. These missions are slow, taking years or decades to reach their destinations, but they are essential because they provide data that cannot be obtained from Earth, close-up observations of worlds that are too distant, too faint, or too complex to study from afar. The exploration of exoplanets, however, presents a different challenge. The nearest exoplanet, Proxima Centauri b, is over 4 light-years away, a distance so vast that even travelling at the speed of light it would take over 4 years to reach it. With current technology, a spacecraft would take tens of thousands of years to make the journey. And yet, there are proposals for interstellar missions, concepts like the Breakthrough Starshot project, which envisions sending tiny lightweight probes to nearby stars using powerful lasers to accelerate them to a significant fraction of the speed of light. Such probes would not carry humans. They would be robotic, autonomous, equipped with cameras and sensors to capture images and data as they fly past their targets. The journey would take decades, and the data would take years to transmit back to Earth. But the effort would be worth it, because it would be the first time humanity has touched another star system, the first time we have seen an exoplanet up close. Now turn your attention to the distant future, to the fate of planets in a universe that is slowly winding down. Stars do not burn forever. They are powered by nuclear fusion, the process of converting hydrogen into helium, and eventually the hydrogen runs out. When a star like our Sun exhausts its fuel, it will expand into a red giant, swallowing the inner planets, including Earth. The outer planets will survive, but they will be scorched, their atmospheres stripped away, their surfaces transformed, and eventually the star will shed its outer layers, leaving behind a white dwarf, a dense, cooling ember that will fade over billions of years. The planets, if any remain, will orbit this dying star in darkness, frozen and silent, relics of a system that once was vibrant and alive. The ultimate fate of the universe is a slow fade into darkness. Stars will continue to form for trillions of years, but eventually the supply of gas and dust will be exhausted, and star formation will cease. The existing stars will burn out, one by one, leaving behind white dwarfs, neutron stars, and black holes. The galaxies will drift apart, carried by the expansion of space, until they are so far separated that light from one can no longer reach another. The universe will become cold, dark, and empty, a vast expanse of space with no light, no heat, no activity. And the planets, those silent wanderers, will continue their orbits, circling dead stars, or drifting alone as rogues, moving through the void with no destination, no purpose, no end. And yet, even in this distant future, there is a kind of peace. The universe does not end in a catastrophe. It does not collapse or explode. It simply fades, slowly, gently, over timescales so vast that they are almost incomprehensible. The planets will continue to exist long after the stars have died, long after the galaxies have dispersed, long after the last light has faded. They will be cold, dark, and silent, but they will be there, monuments to a universe that once was full of energy, full of light, full of possibility. And in that persistence there is a kind of immortality, a recognition that even when everything else is gone, the planets remain, eternal and unchanging. The study of planets, both in our solar system and beyond, is a study of time. It is a study of how worlds form, how they evolve, how they change over billions of years. It is a study of the forces that shape them, the gravity that holds them in orbit, the heat that drives their geology, the light that illuminates their surfaces. And it is a study of the future, of what will happen to these worlds when the stars die, when the universe grows cold, when the last light fades. The planets are not just objects in space. They are records of the past, witnesses to the present, and harbingers of the future. And in studying them, we learn not just about the universe, but about ourselves, about our place in the cosmos, about the fleeting nature of our existence. The silence of the universe, in its final state, is absolute. There is no sound because there is no medium to carry it. There is no light because there are no stars to produce it. There is no motion because there is no energy to drive it. The universe is still, frozen in a state of maximum entropy, a condition from which nothing can change, nothing can emerge. And yet, this silence is not empty. It is full of the memory of what once was, full of the planets that still orbit, full of the structures that still exist, even if they are dark and cold. The silence is not the absence of existence. It is the presence of rest, a final, eternal calm that comes after the long, tumultuous history of the universe. As this final chapter closes, and as you drift towards sleep, consider the journey we have taken. We have travelled from the scorching day sides of hot Jupiters to the frozen night sides of tidally locked worlds. We have seen planets made of diamond, planets with twin suns, planets where it rains glass. We have explored the silence of deep ocean worlds, the loneliness of rogue planets, the beauty of jewel clouds. We have witnessed the extremes of orbital speeds, from years that last hours to seasons that span centuries. And we have traced the history of discovery, from the first exoplanet to the billions we know exist today, and looked ahead to the silent future of the universe. Each planet is a world, each world is unique, and yet all are bound by the same laws, shaped by the same forces, part of the same vast, incomprehensible whole. And in that unity, there is a profound peace, a recognition that we are part of something larger, something eternal, something that will endure long after we are gone. The universe does not hurry. It does not rush. It simply is, and in that simple existence, we find rest.